Hi, Stu Schwartz from MasterMathMentor.com. This is video AB13. The topic is derivative of inverses, and it covers the AB manual pages 65 and 66. In my many years of teaching, it has been my experience that there is no one concept more misunderstood among students and even math teachers than inverses. If you feel comfortable with your knowledge of inverses, you can fast forward to the fifth slide. If not, follow along and get this concept down once and for all. Stop the video and write the inverse to the following terms: 5, boy, dog, hot dog. If you are like most students, you wrote -5, girl, cat, and hamburger, although I have seen for hot dog cold cat. What do we really mean when we talk about an inverse? Most students think of an inverse as the opposite. Now, I might go along with the opposite of 5 is -5, and the opposite of a boy is a girl. But the opposite of a dog is a cat? And the opposite of a hot dog is a hamburger? Why do we think that? Most likely it's because people tend to have either dogs or cats. And at a cookout, people tend to have either a hot dog or a hamburger. But just as those are wrong, -5 for the inverse of 5 and girl for the inverse of boy is also wrong. The reason that all are wrong is that as parts of speech, they are all nouns. You cannot take the opposite of a noun. You can't take the opposite of a bed or the opposite of a car. You can only take opposites of verbs. In math, our verbs are operations, like addition, multiplication, squaring, cubing, taking the sign, and natural log. Write down what you believe to be the inverse operation of each. So, if we start with the operation of addition, the inverse operation is subtraction. The inverse operation to multiplication is division. The inverse operation to squaring is square rooting. The inverse operation to cubing is cube rooting. The inverse operation to taking the sign is taking the inverse sign, not, by the way, taking the cosecant. And the inverse operation to taking the natural log is raising e to a power. So, suppose we are in the current state of being seated. We perform the operation of standing up and immediately perform the inverse operation of sitting down. Our final state is sitting. If we are naked, perform the operation of getting dressed, and then perform the inverse operation of getting undressed, we are back to naked. If we start with 5, add 3, and then immediately subtract 3, we're back to 5. If we start with the number 34, multiply it by 89, and then divide it by 89, we are back to 34. We do not actually have to show 34 times 89 to know that this is true. So if we start with 7.258, square it, and didn't have a calculator, it would take quite a while. But then if we take the square root of the result, we're back to 7.258. So our definition of an inverse function is this: Given some function f, the inverse function f inverse is such so that the following are true. F inverse of f of x equals x, and f of f inverse of x equals x. What this really means is this. Start with x, and pardon the language, if we f it, and then immediately f inverse it, we're left with x. If we start with x and f inverse it, and then immediately f it, we're back to x. Stated another way is that if we have the function f, it will take any x to y. If we have the inverse function f inverse, it will take all the y's back to x. Here's how to find inverse functions. If you are given points in the form x, y, the inverse is all the points yx. So if f of x are the points 0, 4, negative 1, 5, negative 6, 1/2, and 2, 2, then the inverse function is 4, 0, 5, negative 1, 1/2, negative 6, 2, 2. If you are given an equation, replace all the x with y and all the y's with x. So if you are given y is equal to x plus 4 over 2, the inverse is x equals y plus 4 over 2. If you can, and it's not too difficult, you solve for y. In this case, the inverse would be y equals 2x minus 4. Note that f inverse of x is not the same thing as the reciprocal of f of x, or 1 over f of x. That's true with numbers. 4 to the negative 1 is equal to 1 over 4, but not true with operations. One final note. When you graph a function and its inverse, the inverse will be a mirror image of the function across the line y is equal to x. For instance, in the graph, y equals x cubed is blue, y equals the cube root of x is red, and we see the line y equals x in green. And notice that the blue curve is mirrored across that line to give the red curve. Suppose we have the function f of x, y equals x squared, as shown on the graph. The point 2, 4 is on the graph of f. If we take the derivative, we get 2x. So the slope of the tangent line, or the derivative at 2, is equal to 4. Now let's look at the inverse, f inverse of x. We replace the x with y and y with x, and we get x is equal to y squared, or y is equal to square root of x, because we're just working in the first quadrant. So the point 4, 2 is on f inverse. Now when we take the derivative, we get y prime equals 1 over 2 square root of x. When we find y prime of 4, we get 1 over 2 times 2, which is equal to 1/4. Notice that that answer is the reciprocal of the derivative of the function at x is equal to 2. This is not a coincidence. This can be stated by a rule. If y equals f of x passes through the point AB, then f inverse of x passes through the point BA. Then the derivative to f inverse of x at x is equal to b is equal to 1 divided by f prime of x at x is equal to a. This can be stated more compactly. dy dx at the point BA is equal to 1 over dy dx at the point AB. Or f inverse prime of x is equal to 1 over f prime of f inverse of x. I know this sounds confusing. Let's make it much more simple. Typical problems for inverses are usually in this form. Given some function f of x, find the derivative to f inverse of x at x is equal to b, which is the same thing as saying find f inverse of b prime. The meaning of this is as follows. We have an f curve. Therefore, we have an f inverse curve, and it passes through the point BA. You want to find the slope of the tangent to this inverse function at that point. We will find that there are two methods to solve this type of problem. Method 1, shown below, is more straightforward, but unfortunately will not always work. So let's look at problem 2. If y is equal to f of x, which is the square root of x plus 5, find the derivative to f inverse of x at x is equal to 3, which is the same thing as saying find f inverse of 3 prime. Rather than show method 1 and then show the solution to the problem, we will show each step of the method and then switch back to the problem. So step A says to find the inverse by switching x and y. So if y equals the square root of x plus 5, then the inverse is x is equal to the square root of y plus 5. Step B says in this inverse, solve for y. So to solve for y, we will square both sides and get x squared is equal to y plus 5, and therefore y is equal to x squared minus 5. We now have the inverse. So we can take the derivative dy dx of the inverse, and in step C we get y prime is equal to 2x. Finally, step D, we plug in the point B for x in dy dx. So we will now find y prime of 3, which is equal to 2 times 3, which is 6. So in y equals the square root of x plus 5, the derivative of the inverse to that function at 3 has a slope of 6. Problem 3 reads, if f of x is given by y equals x cubed plus x, we want to find f inverse at 10. Although not necessary, it is helpful to see the graph to see what's actually happening. So in blue, we graph f of x equals y equals x cubed plus x. We would like to also draw the inverse, which is x equals y cubed plus y. However, we cannot do this on the calculator unless we solve for y, which would be quite difficult. But the TI-84 does have a command to actually draw the inverse. When we draw the inverse, it's doing really what we normally do to find an inverse, is just switching the x and y points. So you put the function into y1, and from the home screen, you type draw 8, draw in y1, and it will then draw in the inverse. Now, as we see, this is in red, and we want to find the slope of the tangent line to the red curve at x is equal to 10. I show that line in green. And notice that it is a very, very shallow slope. Let's show method 2 to solve this problem. And again, we will switch from the method to the problem so it is clear what's happening. In method 2, the first thing we do is find the inverse by switching x and y. So if the function is y equals x cubed plus x, the inverse is x equals y cubed plus y. This is where the problem comes in. Before, we were able to solve for y. In this case, that is almost impossible to do. So we will now do step B and implicitly differentiate the equation, remembering the chain rule. So we get 1 equals 3y squared dy dx plus dy dx. Step C says to solve for dy dx, and it will be in terms of y. So dy dx is equal to 1 over 3y squared plus 1. Now, step D says to replace x with b in your inverse function and solve for y. Here's what's going on. We'd like to get the value of y to plug in, but unfortunately we were told that x is 10. This function is in terms of y. So what we have to do is, in our inverse function, replace the x with 10. And we get 10 is equal to y cubed plus y. At this point, you look at it and you can eyeball the solution to get y is equal to 2. So our answer, dy dx, the derivative of the inverse, at y is equal to 2, is 1 over 3 times 2 squared plus 1, which is 1 over 3 times 4 plus 1, or 1/13. The slope is very shallow, as shown in the green line. In pre-calculus, you studied functions. We all know how to recognize a function. A function will pass the vertical line test, meaning that wherever you draw a vertical line, it will only intersect the curve at one point. We now introduce the concept of a one-to-one function. In a one-to-one function, not only f is a function, but f inverse is also a function. The example shows y is equal to x cubed as the function in blue, and y equals the cube root of x as the inverse function in red. Y equals x cubed is a one-to-one function because the inverse in red is also a function. There are two ways to determine whether f is one-to-one. You can look at f inverse and determine if it passes the vertical line test. In the example given, the red curve passes the vertical line test. But you don't even have to plot the inverse. You can look at the f curve and determine if it passes the horizontal line test, meaning that if we draw a horizontal line through that curve, it will only intersect the blue curve at one point. If we look at the curve y equals x squared in blue, the inverse is y equals plus or minus the square root of x in red. It is clear that y equals x squared is not a one-to-one function because the inverse in red is not a function. It does not pass the vertical line test. Or if you want, y equals x squared does not pass the horizontal line test. When we work with slopes of tangent lines to inverses, we only want to work with one-to-one functions. If not, we get some ambiguity. For instance, in the example, if you were asked to find the slope of the tangent to the inverse of y is equal to x squared at x is equal to 2, you will realize that there are two possible answers as shown in green. We don't want that, so we will only be working with functions that are one-to-one. Sometimes it's not so obvious. For instance, in function f, you will find that it is one-to-one in the blue section, as it passes the horizontal test in that section. No matter where you draw a horizontal line, it will only intersect the curve at one point. However, it is not one-to-one in the red section. Wherever you draw a horizontal line in the red section, it will intersect the curve at a multiple number of points. You will only be asked to find the equation of tangent lines to inverses on curves that are one-to-one or on sections of functions that are one-to-one. In numbers 4 through 7, you are asked to find the derivative of the inverse to a function at a particular x value. In all cases, we will be using method 2. Method 1, which involves solving for y after we take the inverse, is just too difficult to do. In number 4, you're asked to find the derivative of the inverse to f of x equals 2x cubed plus x squared minus 1 at x is equal to 2. We start by taking the inverse. X is equal to 2y cubed plus y squared minus 1. Again, it is clear that we will be using method 2 because we will not be solving for y. We start by differentiating implicitly, and we get 1 equals 6y squared dy dx plus 2y dy dx. We can factor out the dy dx to get 1 over 6y squared plus 2y. We now have to find the value of y, where 2y cubed plus y squared minus 1 is equal to 2. This becomes 2y cubed plus y squared is equal to 3. And again, you can eyeball the solution and realize that y is equal to 1. So dy dx at y is equal to 1 is equal to 1 over 6 plus 2, or 1/8. In number 5, we have f of x equals e to the 4 minus x, and we're asked to find the derivative of f inverse of negative 3. We start by finding the inverse. X is equal to e to the 4 minus y minus y. Again, it should be clear we will not be solving for y. So we take the derivative implicitly and get 1 equals negative e to the 4 minus y dy dx minus dy dx. And factoring out the dy dx, we get 1 over negative e to the 4 minus y negative 1, which can be written as negative 1 over e to the 4 minus y plus 1. We now set negative 3 equal to e to the 4 minus y minus y. And with the e in the problem, there's only one numerical solution that could work, and that is y equals 4, and it does work. So dy dx at y is equal to 4 is negative 1 over e to the 4 minus 4 plus 1, which is negative 1 over e to the 0 plus 1, and we get a nice answer, negative 1/2. In 6, we're asked to find the derivative to the inverse of f of x equals x cubed minus 4x squared plus 7x minus 1 at x equals 1. We start by taking the inverse. X is equal to y cubed minus 4y squared plus 7y minus 1. Again, we realize we will not be solving for y. So we work implicitly and get 1 equals 3y squared minus 8y plus 7 dy dx, and dy dx is equal to 1 over 3y squared minus 8y plus 7. We then need to find the value of y, where 1 is equal to y cubed minus 4y squared plus 7y minus 1. And we realize that this does not have a nice solution. So we do the problem graphically. We graph y1 equals x cubed minus 4x squared plus 7x minus 1, and y2 is equal to 1. And we find the point of intersection, and we get x is equal to 0.349. Now realize that we are really saying that y equals 0.349. You cannot graph using any variable but x. But the numerical answer to whatever variable you use is 0.349. So dy dx at y equals 0.349 is 1 over 3 times 0.349 squared minus 8 times 0.349 plus 7, and we get 0.219. 7 asks you to find the derivative to the inverse of f of x equals e to the x plus natural log of x at x is equal to 4. We take the inverse and we get x is equal to e to the y plus natural log of y. And again, no way we can solve for y. We work implicitly and we get 1 is equal to e to the y plus 1 over y quantity times dy dx, and dy dx is equal to 1 over e to the y plus 1 over y. I'm going to make no attempt to simplify this fraction. We are now interested where 4 equals e to the y plus natural log of y. So we graph e to the x plus natural log of x and find out where it intersects 4. And we get a value of 1.315. So we then plug that in to our expression dy dx at y equals 1.315 is 1 over e to the 1.315 plus 1 over 1.315, which is 0.223. A problem almost guaranteed to be on the AP exam is like number 8. Given the values of f of x and f prime of x at x is equal to -1 and x is equal to 4, find the equation of the tangent line to the graph of y equals f inverse of x at x is equal to 4. We are given a table with two values of x, -1 and 4. We are also given the values of f of x and f prime of x at those two values of x. To solve this, we see that we are not given any direct information about the inverse function. However, we do know that f of -1 is 4. So it follows that the inverse of f at 4 equals -1, meaning that the point on the inverse is 4, -1. We use the information that the inverse function prime of x is equal to 1 over f prime of the inverse of x. This is a formula that was given to you several slides back and probably should be memorized for a problem like this. So plugging in 4, we get f inverse prime of 4 equals 1 over f prime of f inverse of 4. We just stated that f inverse of 4 is -1. So we are left with 1 over f prime of negative 1. And since f prime of negative 1 is negative 2, our answer is negative 1/2. So our tangent line will now use the point slope formula to say, for the inverse, y plus 1 is equal to negative 1/2 quantity x minus 4. Obviously, this type of problem shows up on multiple choice situations because there are so many answers that could logically be true but are not. With all the notation, it's very easy to get confused when we are taking derivatives of inverses. 18th century mathematician Gottfried Leibniz probably described the rule best when he said quite elegantly, dy dx is simply equal to 1 over dx dy. The good news is that inverses do not appear in abundance on the AP exam. Expect to see several of them, but not anymore.